All right. Hello, everyone. Welcome back to Comp 3430 Operating Systems. I hope that you're all doing okay. It was a bit of a rainy morning this morning, but I guess we need it. I hope you're all doing okay. Today, what I want to talk about in class is I want to finish up with our inconsistent file systems examples. And so I want to go through the process of taking a look at these different possibilities of scenarios of how different data structures in our file system might be updated such that they remain in an inconsistent state, and then being able to identify what an actual person would actually see if they were using the machine that has this inconsistent file system. We're going to really briefly think about how we might try to fix these errors, but the short of it is always trust the inode. The inode is almost always going to be the actual source of truth for what we're trying to do with these things. And we'll think briefly about a couple of different approaches for making sure that we can either fix an inconsistent file system after it's become inconsistent or prevent a file system from becoming inconsistent in the first place. Then what I want to do is move on to process management. So one of the things that we do a lot with our machines and with our computers is that we start programs up. If you're using Windows or Mac OS or a desktop environment in Linux, usually that's like double-clicking on an icon or pressing your Windows key or typing something in Spotlight so that it starts this application up. On the command line, this is usually us typing the name of the program in and sometimes putting / in front of it, and then the program becomes running. This idea of a running program is called a process. This is what we're going to call this idea. It is a process if it is a running program. And so far in terms of being able to create processes in our system, for us, it's been point and click or type stuff in. We're going to ask something to start this process for us. And today, we're going to take a look at how do we write code to cause processes to start? How do I write a program in C that causes another process to start? And the way that this works in general is we are in a running program when our code is running. I will start my program up, and then I'm going to ask the operating system to duplicate me. That's the main thing that we're going to be doing here in terms of using system calls to create processes. Then we're going to use a couple of system calls to manage processes. When I duplicate myself, I want to know when that other process ends. And the other thing I want to be able to do is I want to replace my process with a different program entirely. So I want to be able to start some other program running as opposed to the one that I'm working on right now. As part of this, I want you to be able to do things like describing the life cycle of a process. And so we're going to be taking a look at how processes themselves can have states as they are going through starting up, doing their work, and then exiting. And then the last thing I want us to be able to do is to describe a little bit about how an operating system manages processors, focusing heavily on the idea of data structures. Surprisingly, our operating system, in order to be able to manage running processes, has to have a structure that represents processes. This is a little weird to think about. It is a little weird to think about that there's some structure somewhere in some code that is representing the state of my program as it's running, but this data structure exists. I want to think about this abstractly, and then I want to take a little bit of a quick look at some Linux kernel source code. I think it's really cool to be able to look at some Linux kernel source code because in some cases, the code that we're looking at is literally running in your pocket. If you're not running Linux on your machine right now, then you might have an Android phone, and Android is using the Linux kernel. And so the source code that we're looking at in the Linux kernel is often running in your pocket. And I think that's really cool to be able to see that sort of thing. So first and foremost, I'm going to very quickly remind you of the 4 different options that we have here for the outcome of having an inconsistent file system. We've got a corrupted looking file. So when I open up my file again after this crash has happened, I can still see what was originally there. And the operation that we were doing here, remember, was appending to an existing file. If I open up my picture in Paint again, I will see part of what I originally had, but then some garbage, some stuff that looks like it's not what I had originally drawn, but it just happens to be in the picture that we've got right now. There's less available space on the volume. And so this is where we've got Windows Explorer open up, and we're taking a look at our C drive, and it used to be 96% free, and now it's 95% free because there's a little bit of extra space taken up. The size of the file in bytes has increased. So the file's size is reported as bigger. And then the last option here is that there's no observable change. We're not able to actually see anything with the tools that we've got to interact with our machine after this has become inconsistent. So I'll give you a couple of seconds to join up to this Mentimeter, and then we will get back into this quiz. I'm going to pop over to the slides right now. And our very first question here is, what would our human operator see if we crashed after updating just the data region or the cluster heap? So with VSFS, we've got this data region that's full of blocks, and with EXFAT, we've got the cluster heap itself that keeps the data for our files. I'm going to give you 5 seconds to answer this question. 1, 2, 3, 4, 5. I'm going to show the responses here. Okay, so no observable change is the biggest answer. And that is indeed the correct answer here. If I write the data to the data region, if I write the cluster in the cluster heap, and I don't make any changes to the metadata for this file or metadata for the file system itself, when I open this up in Paint, if I read the stream extension for the first cluster and the size of the file, it's still the same. So I'm only going to read up to that many bytes. I'm not going to even bother looking at the new data that was there. If I'm doing this with VSFS, I haven't added a new block to my direct block pointers. So I'm going to read up until the direct block pointers that I got, and I'm going to stop because I haven't made any changes to that inode structure. Is this file system inconsistent? I'm going to give you 3 seconds. 1, 2, 3. Was a little bit split here. This file system is not inconsistent. It is not inconsistent. We've written the data to the disk in the cluster heap or the data region, but we haven't actually modified any of the metadata. And remember that inconsistency in our file system is purely about the metadata. The data itself, while if we lose that information is bad for the person that's actually trying to do this stuff, the metadata itself is what's actually the most important part in terms of considering file system inconsistency. Here's another scenario. What would our human operator see if we crashed after updating just the data bitmap and the inode or directory entry? So our allocation structure and the actual metadata for the file itself. I'm going to give you 5 seconds to answer this question. 1, 2, 3, 4, 5. And we've got a pretty even split here. And yes, in this case, it is all of these things. If we've updated the data bitmap and the allocation structure, the amount of available disk space that's going to be reported by our system is going to be slightly less, assuming that our system is using that allocation structure to measure how much free space there is. The size of the file will have changed because we've updated the metadata for the file itself. And the image will appear corrupted because we haven't actually written the data to the data region or to the cluster heap itself. Is this file system inconsistent? I'm going to give you 3 seconds. 1, 2, 3. And no, this file system is not inconsistent. Double negatives here. It's not inconsistent. This file system is consistent. This file system's consistent because all the data structures agree with each other. All the data structures agree with each other about what the metadata is for the file and for the file system itself. What would our human operator see if we crashed after updating the inode and the data region or the cluster heap? So we actually got to write the block, and we were able to write the inode or directory entry, but we were not able to write the data to the data region. Sorry, not able to write the allocation structure. I'm going to give you 5 seconds to answer this question. 1, 2, 3, 4, 5. Well, this one's pretty split, so we think we're going to see a bigger file size, and that much is true. We're not going to see a corrupted image here because we have written the data. We actually persisted the data to the data region or to the cluster heap this time. So while we have updated the size of the file and we've updated the number of the direct block pointers, we will have be able to see the file's actually updated data because we actually updated it. We're also not going to see any less available disk space because we did not update that allocation structure. And again, assuming that the OS or our file explorer is using the allocation structure to tell us how much free space there is on this volume, we didn't update it, so it's not going to be able to see that change. Is this file system inconsistent? I'm going to give you 3 seconds to answer this question. 1, 2, 3. Yeah, 100%. This file system is definitely inconsistent now. So there are going to be at least 2 data structures here that do not agree with each other about what the state of our file system is based on the metadata. What would our human operator see? And this is the same condition here. So I've updated the inode or directory entry, and I've updated the data region or the cluster heap, but some amount of time has passed. So let's say 30 minutes go by, and there's other people that are also using the system at the same time as I am. I'm going to give you 2 seconds to think about this. And then I'm going to give you 5 seconds to answer the question. So 1, 2, 3, 4, 5. Some time has passed. We've updated the inode and directory entry, and we've updated the data region. After a little while, we're probably going to see a corrupted image. And now let's think about this order of operations here again, about what we're doing when we're making changes to our files. One of the steps was, I need to find a free block, or I need to find a free cluster. And the mechanism that we were going through, or the data structure that we were going through to find that free block or free cluster, was to go through that allocation structure. This is the tool that I was using to say block 7 is free. If I'm in a situation like this one, where I've updated the direct block pointers in my inode, and I've actually written the data to the disk, initially, when I open that file, I'm going to see what I expected to see. I've got this new picture of my cat and this new picture that includes me in the photo that I've adjusted here. But eventually, I'm going to open up Microsoft Word, and I'm going to write, "Dear Diary, Walter bit me today because he wanted to go outside really badly, and I just wouldn't let him go outside." And then I'm going to hit Save in Microsoft Word, and the whole process here is going to find this free block that has not been marked as allocated. Even though I wrote to it previously, it hasn't been marked as allocated. And so Word is going to save part of "Dear Diary, Walter bit me today" in this part. And so when I open up my picture in Paint again, that new thing that I added, because it was not marked as used by the allocation structure, has been overwritten by some other application or by some other code. And so when I open it eventually, what I'm going to see is this corrupted image. Is that okay with everybody? Yeah. Yes, that is a good point. This is assuming that a file system check, and we haven't tried to repair the file system in any way in between the file system becoming inconsistent and then this new thing starting to happen. Yes. The most likely cause of file systems becoming inconsistent is that the power gets yanked, or lightning strikes, or Windows blue screen of death, right? That sort of thing starts to happen. And oftentimes what happens when our machine comes up is we get a file system check. It's going to go through the process of trying to see, is this file system in an inconsistent state now? So this is a contrived example. This is a contrived example of maybe I've written some buggy code that does not update all the data structures, but it doesn't cause the system to crash. Yeah. Maybe Walter's just really mad and yanking the cord himself, right? Yeah. Any other questions? All right, awesome. Okay. Here is my last question about file system consistency. And this is specifically about exFAT. What would we see if I crashed after renaming a file? So this is a different operation than what we've been doing so far. And when I'm renaming this file, I'm trying to make the name of the file longer than it was before. So our stream extension tells us how many characters are in the file name. And I've been able to update the stream extension, but I was not able to update the file name. And I'm going to contrive the situation by saying that the stream extension was the last directory entry in a cluster, and the file name is somewhere else. And so it's not going to be within a single sector. I'm not going to be able to atomically write these things. I have to do one, and then I have to do the other, somewhere else that's far away. What would we see if this were to happen? So I'm going to give you 2 seconds to think about this. And then I'm going to give you 5 seconds to answer. So 1, 2, 3, 4, 5. And lots of people are picking this. Good, yes, lots of people are picking this. Yeah, absolutely. This is what we would start to see. I mean, I don't know about exactly that, but we'd start to see something that looks like a really messed up file name. Part of what would begin to happen here, and I'm starting to think about how my own code works working with exFAT, is I'm going to get to this stream extension that says there's 37 characters in this file name now. And so that says to me that there are 3 file name directory entries that should be here. Alternatively, there used to be 8 characters, and now there's 15. And if that hasn't been zeroed correctly, then we'll get to this state. But my specific thought is about there's 37 characters, and there used to be only 15. So now I should expect there to be more file name directory entries than there used to be. And if I don't make changes to the rest of my directory entries for this specific file, what I'm going to start doing is trying to treat stream extensions as file names, and we're going to get this messed up file name situation here. Is that okay with everybody? How is everybody doing today? Coffee, yes, coffee, yeah, yes.
So basically you're saying that the data when will be updated, and that when we read it, let's say it's 10 characters and the actual file name is still 5.
Yeah.
That we're going into the next directory entry, and we're reading it as if it's a file name.
Well, so there's 2 situations here. One is in the situation you're describing, where we have fewer than 15 total characters. We might just be reading extra stuff that wasn't initialized in the file name previously. So if I go from 5 characters in my file name to 10 characters in my file name, both of those will still fit within a single file name stream extension, file name directory entry, sorry. But we don't necessarily know that this has been initialized previously to 0. If it were previously initialized to 0, we'd still just see the original file name printed out because there's a bunch of null bytes that are appearing after that. If it wasn't previously initialized to 0, which is not a guarantee that we can assume, we'll start to have extra characters appearing after it. We don't know what they are because they're just going to be whatever ASCII or Unicode characters get interpreted from the bits that we've got there. The other case that I'm thinking about is I've gone from 5 characters to 20 characters. And now there should be 2 file name entries for this thing as opposed to just 1. And so if I read one entry and then I read the next entry and I just blindly assume that they're file names because the stream extension told me the next 2 things should be file name entries, I might be misinterpreting one of the other kinds of one of the other kinds of directory entries as characters. Yeah. All right, okay. So what I want to briefly think about now is how do we get out of this state? So I'm going to go back to this point right here. What would our human operator see if we crashed after updating just the data bitmap and the inode or directory entry? I'm going to go back to here. I'm going to escape this, and we're going to come back to this, but I want to pick a specific one here. So here's the one that I'm specifically thinking of. I want to unskip this slide, and I want to present again. What would our human operator see if we crashed after just updating the FAT? So now this is an EXFAT specific scenario that we're looking at. Our textbook describes 2 approaches to dealing with inconsistent file systems. One is file system checking, which you brought up, which you were right to bring up. You're definitely right to bring up here. And the other one is called journaling. File system checking, just for kind of brief definition here, the idea is I know that I've crashed. I somehow know that I've crashed my system, and so I'm going to go through every single data structure in this file system and check to see if they are all consistent with each other. We could write code to do that today in class, but that would be painfully tedious. It would be so painful to do that, and I really don't want to. I really don't want to. I really don't want to. If we're in a situation like this, where we've crashed after just updating the FAT in EXFAT. To me, the best place to go to find out what the actual state is to begin to find all of our directory entries. And this is finding every directory entry for every file and every folder in the system. So going through in memory, building up which clusters are actually used by the stream extensions, which are the first clusters that we've got. And use the file size to determine whether or not the FAT should be updated, whether the FAT is consistent or whether the FAT is true. Can I count up the number of clusters that I've got in this thing? Ultimately, what we would find if we've just updated the FAT is that one of our cluster chains is 1 longer than it's supposed to be because the stream extension's data length will not have been updated yet. And for me, this is now going to be a decision of, do you trust the FAT to say that there is actually another cluster here, or do you trust the directory entry that says it's this many bytes that are left in the file, or that there are this many total bytes in the file? If I trust the FAT, the result of this is going to be, I'm going to change the file size, and I'm just going to have to add the full size of the cluster to this thing. And the result might be a corrupted file from the perspective of the operator. If the person is sitting there and opening up a Microsoft Word file and there's extra bytes at the end of it, I don't personally know how Microsoft Word will behave in that situation, but it might not like that there's extra stuff there that doesn't actually have anything to do with the Word file that we've got. If I say, I'm just going to change the FAT so that I just remove that cluster. I'm just going to say FFFFFFFF like this. Then that, in my mind, is making our file system consistent to remove the last cluster from this thing, or the last n clusters from this thing that we've got, if we've only updated the FAT. File system checking it's happened. And now I need to try and make my file system data structures consistent. To me, generally, the canonical source of truth for these things is the metadata for the file. directory entries or the inode itself, and then we update the other data structures based on that. Journaling, how many of you have taken databases already? Many of you have taken databases already. Awesome. Do you remember the word transaction? Yes. The idea of a transaction in SQL is that you start a transaction, you do a bunch of updates, and then you end the transaction. And then everything that is between the start of transaction and end of transaction must be applied to the state of the database that we've got. Part of this is about concurrency. I don't want to have different people doing different things at the same time. That's going to be a problem that we'll see later in this course too, but I don't want to have different people doing different things at the same time. Journaling is, let's try to make sure that file system inconsistency cannot happen in the first place. Journaling is, rather than writing directly to the data structures in the file system, I'm going to start a transaction somewhere, and then I'm going to make the changes that I want to do in that transaction somewhere else that's not actually the data structures, mark it as finished, and then replay that transaction. When my system is coming back up again, I'm able to make the changes even if I'm halfway through changing them in the first place. So both of these are described in our textbook in terms of file system checking and journaling. And this is about as much time as I'm going to spend in class talking about them. It's the textbook that we're going to be relying on for most of this stuff. Are there any other questions about file systems in general? What's my favorite part of the file system? Which one? EXFAT. It's the cluster chain batch. It's the bat. Yeah, I don't know. That's a weird question. What's your favorite part of a cat? Yeah, yes. That is an excellent question, and I'm so happy that you asked that because somebody else asked that same question last class, and I want to talk about it, and so I'm going to talk about it. Here is EXFAT. We all know it, we all love it, and here it is again. Let's say that I've got my picture of Walter here, down at the bottom in clusters 8 and 9. The way that we know that my picture of Walter here starts at cluster 8 and 9 is because my file is contained within the directory entries for this directory. And the way that I'm able to find that file in the first place is that the stream extension says it starts at cluster 8. Deleting the file might look like this. And deleting the file might look like this. I'm going to write just F here, and I'm going to draw an arrow to say I'm just filling these all up with Fs. They're not cluster chains anymore. But I didn't delete the actual data for the file. I just removed the directory entry for this thing. As far as you are concerned, as far as I'm concerned, as far as my mom and dad are concerned, when they open up Windows Explorer, that file's not there anymore. But the data is still on the disk. The data is still in the cluster heap. Pictures like this will start with JPEGs. If it's a JPEG, it will start with a JPEG magic number in the same way that ext2 had this magic number and in the same way that EXFAT has this signature, but it's a magic number that says this is a valid file system. I don't remember what the magic number for JPEG is, so I'm just going to say that it is BEEF. That's the magic number for JPEG. An image recovery tool or a file recovery tool will start scanning the cluster heap. It's not going to look at the FAT. It's not going to look at the directory entries. It's just going to start scanning the cluster heap. And it's going to go to all of the clusters in the cluster heap, and it will be able to recognize things like This cluster has things that look like directory entries because I can see that this one has the file entry type, and then 32 bytes later is the stream extension entry type. And I'm able to figure out that that's what this is. I'm going to scan this one, and I'm going to see that there's some ASCII text here. The bytes are contained within the range of printable ASCII text. So this cluster probably contains a text file. I'm going to get to this point, and it's got this magic number that is for JPEG files. So this probably contains an image. I'm also further able to do things like, does cluster 4 have any entry in here? Does cluster 8 have any entry in here? And alternatively, does cluster 4 and 8 have any entry in the directory entries that we've got here? Some file systems will just not delete the data from the file system. They'll just erase the metadata about the files. And that's how we're able to do some kind of basic recovery. The problem here is that as part of this delete operation, where I've just stricken these things from the file system with allocation structures, they're also marking these clusters as free for use. And so the advice generally for file and image recovery software is do it as fast as possible. Like, don't let other stuff run, because as soon as other stuff starts to write to the disk, those clusters are free as far as that other software is concerned. And it will begin to overwrite the data that you've got there. Yeah. So that's a great question. Thank you for asking. And thank you for asking last class. Yeah. Yes. The question is, do we need to know exFAT for the term test? I'm going to talk about the term test on Tuesday of next week. So remember, this is a long weekend that we're coming up to. So I'll talk about the term test on Tuesday next week. But in terms of the file systems that we're looking at, the learning outcomes that I am expecting you to be able to demonstrate are show how common file operations, show how the data structures in file systems, and I might be misphrasing this, sorry, but show how the data structures in file systems are changed or modified based on common file operations. So for you to be able to do something like that with ext2 or exFAT is something that I would expect you to be able to do. I don't expect you to be able to write code. I think it's safe for me to assume that many or all of you are spending lots of hours doing code to do this exact thing. And I don't want you to write that C code on the tests again. That would be over the top. I don't want to do anything like that. It would be more of a high-level description of what data structures are being used, referred to, changed, updated, how they're being changed, that sort of thing. The test is in 8 days. Yes. It's on Friday next week. Yeah. Yes. My plan was to post one tomorrow, yes. Yeah. So I'm going to post the, I'm basically just taking the term test that I gave last term and I'm putting it up on the course webpage for you, yes. Yeah. That should be fairly early tomorrow, but it will be before the weekend, yes. I'll spend more time talking about the test on Tuesday. I want to let you focus on the assignment before talking about that. All right, okay. I lament that we're leaving file systems because it is one of my personal favorite parts of this course. But alas, there's more to operating systems than just putting files on a disk. So we're going to spend time now thinking about processes. We're going to spend time thinking about how our operating system is able to start processes, what kinds of data structures it uses to represent processes, and then the kinds of information that an operating system would need to know to be able to do that. I want to start here by talking about something that is maybe a little bit outside of the idea of processes. And it will lead us to what we're thinking about today, but on machines in the terminal, there are 3 different streams of text. And you have used at least 2 of these in your courses before. There's standard input. This is where we're getting data for the course. This is where we're getting data from our keyboards. So thinking all the way back to comp 1010, this is like doing new scanner system.in. System.in is standard input. In C, you might have done this with fgetS and using stdin as the source of data for where you're getting stuff. Standard out is literally the terminal. This is where I'm printing stuff out. And in terms of like ancient times, standard input was literally a typewriter, and standard output was quite literally a printer, an actual physical printer that would show the output of this stuff. Standard output, you definitely have done standard output stuff. In Java, it's actually named system.out, which implies it is standard output. In C, most of the work that you've done is with printf, which doesn't say standard output, but printf is a shortcut for fprintf, stdout. They do the same thing. In this course, I've referred to this idea of standard error, and you might have used standard error before. Standard error is a third stream that is also an output stream that is just different from standard output. And it makes it easier to then see the difference between output that's being printed because of an error and output that's just meant to be regular output. These three different kinds of input and output streams have file names that you have used in C previously, but they also have corresponding file descriptor numbers. So stdin is what you would have used for fgetS. When you're doing read on your file system, you're passing a file descriptor, which is an integer, and stdin file no is also an integer that you can use to pass to a function like read to get input from standard input. When you're doing printf, you're printing to standard output. You haven't used write too much or at all in this course. You haven't used write at all in this course, but write is a system call that you can use and pass a file descriptor to it to write data to a file. Standard out file no is an integer that represents the file descriptor for standard output. And standard error file no is the same general idea for standard error. What I would like to do is I'd like to write a tiny little C program that does some basic standard input and standard output, some basic I/O, and not really very much at all. I've put some files into a repository on Git. I've linked to this to GitLab. I've linked to this in today's lecture notes. But the repository here is https://code.cs.umanitoba.ca/comp3430 summer 2025 /process-management. The code that I've got there, if I could spell this, mint. If I could spell this correctly, the code that I've got there is pretty minimal. There's four files in total here. There's a make file that looks pretty much like what you've seen in the make files that I've given you so far. There's basic IO, there's process management.c, and there's a README file, which I'm going to verbally describe to you as opposed to reading it to you from the README itself. So I'm going to open up basicio.c, and basicio.c doesn't have anything in it. It's a basic skeleton program. I want to do some very basic I/O in this thing. And so what I'm going to write is this. I'm going to write char buffer is equal to the null byte. I'm going to say printf, enter a character, and press enter or control D. I'm going to say buffer is equal to getChar. This gets input from standard inputs. And then I'm going to write putChar buffer. And at the end, I will exit successfully. I'm going to pop open a new terminal below this one. This main program fits nicely. on one single screen. I'm going to make this, and I'm going to run basic I/O. Oh, I got to save it first. I'm going to save it. I'm going to make it, and I'm going to run basic I/O. All right. What's a good letter?
R.
Thank you. R. Uppercase or lowercase? Lowercase r. Enter. We did it. Yes. Good. Excellent. I've written a nice little basic program in C that will get one single character and print it back out to standard output. Why? Why though? Why are we doing this? This is the second time in class I've been like, why? Why are we doing this? Why are we doing this? I want to do this again, but I want to think about this in the context of a couple of different ideas. The first idea that I want to think about is mode switching. And the other idea I want to think about is system calls. You all have already done some system calls. You have been doing lseek and you've been doing read. These sure look like functions from our perspective, and they are indeed functions that we are calling. But the difference between a system call and a regular function call is that we're not just putting something on the stack. When I call a function in C, when I call a function in Java, a method in Java, when I call a function in Python or a method in Python, I'm adding a new stack frame. And there's a bunch of stuff that goes in that stack frame that is related to the function that I'm currently running. A system call is similar. We invoke it the same way, but the difference is a system call is asking our operating system to do something for us. And the way that we're doing this, please operating system, do this thing for me, is a series of mode switches, so to our operating system space and then back to our user space. So I'm going to think about these two keywords, user space and kernel or OS space. And the reason for us wanting to do this mode switching is our operating system has to be able to do privileged stuff. It has to be able to do stuff that regular user programs should not be able to do. As an example, I want to be able to print something to my terminal. I want to be able to print to my terminal. I don't want you all to be able to print to my terminal. I want to print to my terminal, and I don't want anyone else to be able to print to it. And so I have to politely ask my operating system to do that. And that itself is a privileged operation. This is something that the OS has the privilege to do, but not me. I can politely ask for it to happen, but the operating system is ultimately what's responsible for doing that. The other thing that I want to think about is the state of this program as it is running. And we're going to use a program that's called PS to be able to take a look at the state. So the first thing I want to do here is I'm going to go back to my terminal. And what I want to run is a program that's called strace. Strace is a program that's only available on Linux, sorry. So if you're using Windows Subsystem for Linux, you can use this in your Windows Subsystem for Linux. If you're using Lima, you can do it in Lima, but you won't be able to do it in like the Mac OS terminal directly. So strace is something that you'll have to use Linux for to be able to have it work. I'm going to run strace, and I'm going to say strace basic IO. And when I run this, what we're going to see is all of the system calls that are being invoked by the process. So when I do /basic IO, I'm asking for this process to be created. When I run strace here, what I'm asking for is I want you to print out every system call that's being made by this program. I'm going to zoom into this panel here, and I'm going to hit enter on my keyboard. There's a lot of output here. There is a ton of output, which is a little surprising given how small this program was in the first place. Like it did two things. It did three things. It printed with printf, and then it did getchar, and then it did putchar, and then it exited. And yet there's a whole ton of stuff here that's happening before this. For now, we're going to ignore it, all of it. We're going to ignore everything that's there except for a couple things. The first thing that we're not going to ignore is this line right here. It says right. And the first argument that it's passing to right is the number 1. I'm going to zoom out of this. I'm going to open a new terminal to the side over here. I'm going to zoom into this one. I'm going to take a look at man to right. So this says, I would like you to write to a file descriptor, please. Write is the system call that you'd make to write to any file in your system. So anything that's in any file system is something that we would use write to be able to make changes to. This is a system call that we're making, and we're politely asking our OS to be able to write to a file. The first argument that we see showing up in write here is the file descriptor that we want to write to. And in this case, the number 1 appears there. The number 1 in this case represents standard output. This represents standard output. This represents standard output in some part of the process's structures underneath what the operating system is actually doing here. The second thing is the buffer. This is the thing that we want to print out, and then this is the size, or the number of bytes that we want to print. I'm going to zoom out here. I'm going to go back down here, and we can see that we've got write. It's got all this stuff here, and it says 45. That's the number of characters that we actually put into the message that we're asking to print out with printf. And then there's a read. I'm going to hit Control-C here, and I'm going to start this again because resizing my terminal did stuff that I don't really want to see right now. Then there's a read. You are familiar with read. The first argument that you pass to it is the file descriptor. The second argument that you pass is the buffer that you want to write into. At each of these points, when I call write, we have to go through this process of doing this mode switch. I'm going to set stuff up so that I can ask the operating system, hey, please do this for me. Then the OS takes over. We're kind of going through our hardware to get to this point. The OS takes over. It will do what we're asking it to do, and then it will return to us and say, equals 45. Yes, I did write 45 bytes to the file descriptor that you asked me to. Once we come back from the OS does this through hardware, where it's going to switch modes from operating system space mode or kernel space mode back to user mode, and we get to take over again. At that point, I'm going to say read. I want to read from file descriptor 0, which is standard input. And now I'm stuck. My program has been kind of put to sleep at this point. I am waiting. The key word here, and this is a word that I'm going to start using regularly, is that my program is blocked. My program is currently blocked. It's not able to proceed. The line that we are currently blocked on in the source code that we just wrote here is line number 10. We're stuck. We are blocked. We cannot proceed past this point because our OS has not said, here's the data. Here's the thing that you asked for. So we're stuck. The state that our process is in right now is that we're sleeping and the operating system is doing something. The OS is also waiting for us to actually type stuff in on the keyboard, but as far as we are concerned from our process's perspective, we are sleeping and we're in OS mode. The OS is waiting for something to happen. When I start typing characters on my keyboard, so I'm going to type in lowercase r again here, and then I'm going to hit Control-D on my keyboard. What I get is the read succeeds. The read succeeds, and our OS is going to return control back to us. So we're going to go from this OS or kernel mode back down to user mode. And the data that we asked for is going to get put into our buffer. We asked here, surprisingly, for 1 kilobyte of data with getchar, which is weird. I didn't make that choice. My standard library made that choice for me. But we asked for a kilobyte of data, and our operating system said, here's 1 byte. Here you go. Have 1 byte worth of data. And then after that, I called putchar. And so I have to go through that entire process again. I have to go from my program, I have to set stuff up so that I can ask the hardware, please raise this to the OS. The OS then takes over and does that action on our behalf. It puts the R onto our terminal, and then it will eventually return control back to us and say, okay, I wrote 1 single byte of data. At the end here of my program, what I'm doing is return exit success. And that's the very last system call that we can see here, exit group. Exit group is saying, I'm all done. And 0 here is the actual value that we have in exit success. That value for that integer is 0. I've successfully exited from this program. I'm going to run my program here, basic IO. And I'm going to open up a new tab, and I'm going to run PS. PS is a program that will print out the state or the running processes that we've got on our system. I'm going to zoom in on this, and I'm going to run PSA. PSA shows us a bunch of interesting stuff. The first is here. This column represents this ID, this number. This is a unique identifier for the processes that are running on our system. This is called the process ID. This number uniquely represents every single process that is currently running on the system. Way down here is where my process basic IO is running, and it currently has process ID 1160156. I'm going to zoom out here. I'm going to hit Control-C. I'm going to run this again, and I'm going to run PS again. When I run it again, now it's 1160411. So each time I run a process, every process is going to get its own unique ID on the system that I'm running it on. The second column here, this is labeled TTY, and what we see here is PTS/3. And I have a bunch of these different PTS numbers showing up in my system. TTY stands for teletype. And when I said literally a printer, I meant literally a printer. A teletype is literally a printer. It's actually a printer. I don't know if you've ever heard this before. Have any of you actually heard dot matrix printers before? Do you know what a dot matrix printer is? That's not quite what I wanted to see. I'm going to go to Wikipedia, and I want to search for dot matrix. Yeah. Dot matrix printers were these printers that printed out stuff that looked a little bit like that. And the way that they sound will go all the way through the history of printing. There's this thing that's moving across the paper, kind of like a regular bubble jet printer looks like, or an inkjet printer, except instead of like spitting ink out, it operates like a typewriter where it's literally slamming against the paper and a ribbon of ink. And the way that these things sound is they just go like buzz, buzz, buzz across the page over and over and over again. And at the university, we used to have these dot matrix printers, and they were free for students to use, which was great. Except students realized that, and they would inevitably start printing out lines on their paper. Rather than just going to the store and buying lined paper, they'd just print out a bunch of lines on paper. Because it was free, so why not? So this idea of a teletype here, and I'm actually going to go back to Wikipedia because I do want to do this. A teletype, and we've got one of these actual machines upstairs. This is a teletype. So it's a keyboard, and it's got a printer attached to it. And the idea with this is that we didn't have screens. We had typewriters and printers, and I would type my command in, and then the printer would spit a bunch of stuff out that represented what was printed to standard outputs. So the TTY here represents effectively the terminal window that I'm looking at now. PTS here stands for pseudo terminal. This one here is the important one for me. When our process started, it was in a state of running. So I'm going to zoom out of PS's output here, and I'm going to take a look at our program again. When our program started, so when we initially got into our main function here, our process was in a running state. We did whatever this line of code's assembly language instructions were. We did whatever this line of code's assembly language instructions were, which included doing the mode switch and going to OS space and coming back down into user space. And then we got to this line right here, where we started to do some assembly language instructions. We went to OS space, and the OS said, okay, you are waiting for something, so I'm going to put you in a sleeping state or a blocked state. S+ here in Linux says, you are sleeping right now. You're blocked. You can't do anything. So I'm just going to put you into the state. And we'll talk about scheduling later, but I'm not going to let you run on the processor until I have more information for you to do something with. As soon as I press enter on my keyboard here, we're going to get unblocked. And we're going to start running instructions again. We're going to go back into this running state. And then eventually we will go into an exit state as our process leaves. So my terminal takes control again, or my shell takes control again. So what we've seen here is that we've got system calls that are taking place underneath of the functions that we're invoking. So putchar and getchar and printf are actually doing these system calls. And for each of these different system calls, we're doing this mode switching part. We're able to inspect some of the state with our process. And the new keyword here that we've got is that in some situations, our process is going to become blocked. We won't be able to do anything. So our operating system is going to change the state of my process to a blocked state. This is cool, but it's basic I/O. And I want to actually start being able to do some process management stuff. So far, in terms of process management, our shell is doing process management for us. The shell, just to be clear, in this case is the thing that prints this stuff out, and it's waiting for me to type something in. My shell is called fish, the friendly interactive shell. This is a C++ program that is waiting for me to type stuff in, and it will start to do stuff on my behalf. The shell that you have on Aviary is called TC shell. I don't know what TC stands for, but it's the TC shell, and it's from 1977. I think that's when it started being developed, as 1977. The shell that you might be running on Mac OS is called Z shell, or Z shell for our American friends. And the shell that you're running on Windows Subsystem for Linux is called Bash. This is called the Born Again shell. All of these are different programs that will do process management for us. And so far our shell is doing all of this process management for us. Now I want to write a small program that's going to do some basic process management for us. We've seen this idea of a process ID, but we're going to have to use this process ID in code. We're going to have to add some new vocabulary about the idea of processes themselves. Processes have relationships to each other, and we call them parent and child in terms of the relationship that processes have with each other, which is unfortunate because we're eventually going to start to talk about parents killing their children, which is not exactly a thrilling thing to talk about, but it is something that we're going to talk about. And then finally, what relationship these different processes share with one another. So I'm going to go back to my terminal. I'm going to zoom out here, and I'm going to close some of these, turn off caps lock. I'm going to close some of these other terminals because I don't need to have them all open right now. I'm going to quit out of basicio.c. I'm going to start editing process management.c. Process management.c in it has nothing right now. It's the same sort of thing as what we had with basic IO. The very first thing that I'm going to do with this, and I'm going to ask you to accept this as the truth for now and not question me. Let's just do it this way for now. This will become important for us later. The very first thing that I'm going to do is I'm going to change the signature of my main function. Previously, I've been writing void to say I don't want to accept any arguments. I don't want any arguments on the command line. You might have seen stuff that looks like this before, int argc and char star argv with square brackets. This is how we get command line options passed to us. But I'm actually going to add a third option. This is the part that I just want you to accept and not question, and we'll talk about it a little bit later. The third thing that we're going to accept here is called char envp. It is also an array of strings. We're going to need this later. We're never actually going to use it, but we're going to need it later for some of the stuff that we're going to be doing with process management. I can spend a little bit more time talking about it in a later class. The first thing that I want to do with this is I want to start being able to cause a new process to be created. The function or the system call that we're going to use for this is called fork. So I'm going to say man fork. Fork is the system call that we're using to create a child process. I'm going to have to add a new include to the top of my file here, unistd.h. And the signature here is it accepts no arguments. It's called fork, and it returns this type PID-T. PID-T is just a number. It's just a number, but it's a special type that's saying this is a number that represents a running process. So if we were to look at the actual source code for this, ultimately PID-T would just be typedeft as like an int64 or something. It's just a number. It's just a plain number. What fork returns is the process ID of the child process. So I'm going to say this, PID-T child process is equal to -1 for now. I'm just going to initialize this to some value that is not possible. We don't ever have negative process IDs in our system. I'm also going to make sure that our code compiles, cast all these things to void, because I'm not actually going to use them for now. We're not using these arguments yet. I'm going to say printf, hello world, new line. So this is nothing quite new compared to what we've seen before. And now I'm going to say child process is equal to fork. So fork returns an instance of this PID-T. It doesn't take any arguments. I'm going to say printf, hello again, %d, new line, child process. And then I'm going to allow this to exit. I want you to take one moment here. I'm going to make this code, and I would like you to think, I'd like you to predict the output in your head, just thinking about it. What might we expect to see showing up as output from this? Okay, I'm going to run it. So I'm going to run process management. And we have 3 lines of output. What we've got is that on line 13, our process that I started here by typing in /process management prints out hello world. So I've got one process that's running that prints that out. On line 15, I'm saying fork. The fork operation is taking this running process and it is duplicating it. After that line returns, so we're doing this entire song and dance of, I'm going to go to my operating system space. I'm asking, please fork, please duplicate this thing that represents me as a process. My operating system will do what it needs to do, and then it will return control, but to two processes, not just one. After this line, after line 15, two running processes. Before this line, one running process. After line 15, we're going to have two different processes. One prints out hello again, and it prints out a number here. And the other one prints out hello again, but it prints out 0. The idea with this is that when we call fork, it's going to return control to two different processes. We are able to know in our own code which process we are currently running in based on the return value here. We have two running processes. In the parent, child process or child PID, the process ID that we get back from fork, child process contains the PID, the process ID of the child process that we launched. In the child process contains 0. So the parent process is going to be the one that has a non-zero return value from this. That's going to be the one that I originally asked to be launched when I did /process management. The other one is going to be the child process. And so normally what we do with this is after we do fork, we ask a question. If child process is equal to 0, hello from child, else hello from parent. And what I'm going to say here is not child process, but I'm going to use a different function called. It's called getPID. GetPID is a function that we can use to ask, what's my process ID? So getPID is, what is my process ID? GetPPID is get the parent's process ID. So I'm going to write one additional thing here, printf. I am the child of %d \n getPPID. And these two functions are coming here from UniSTD, so we don't have to add anything because we just added that from fork. So I'm going to make this, and I'm going to run it one more time. And so what we've got here is our child process and our parent process are going to diverge at this point. I want to be like 1,000,000% clear that we're making a copy of the same process. So at line 15, we're duplicating everything about the running process that we've just started. On line 23, both of our processes are going to run this comparison. They will both run the instructions here, but the value that we have in each of these is going to be a little bit different. In the child process, the one that has fork returning 0, we're going to run these instructions, and in the parent process, we're going to run this instruction. So we're using this conditional statement to ask what's the value of this thing, but both of these two different processes are running the same code. I'm going to add one thing here, and I'm going to say int value is equal to 42. I'm going to say printf the value of value is %d. I'm going to make this, and I'm going to run it. The order of output here is a little bit messed up, but the value of value is 42, and the value of value is 42. That adds up. We've got these two processes that are running. They're both running this printf statement. They both have the same value here. I'm going to even modify this just a little bit further in %d, and I'm going to say get PID. I'm going to make this, and I'm going to run it. We have two different process IDs here. They're both printing out the same value for value. And I'm going to do one final thing here. I'm going to say value is equal to, what's another good number? Why 80? That's not a very good number. 80, that's a fine number, thank you. The value of value is now 80. I'm going to make this, stop, think about this for a second, predict the output. There's these two lines where we're printing out the value of that thing. I'm going to run this. On the line where we're doing fork, here, we are duplicating the running process. When we duplicate the running process, we're duplicating everything about the running process. Our running program, our process, has memory that's attached to it. It's got space that it's able to do stuff in. It has a stack. The stack in our process has space for an integer here. On line 16, when I do the fork, I'm duplicating everything. I'm duplicating the program's code in memory, and I'm duplicating the stack that is currently being used for this program. And when I get to this point here where I say in the child process, I'm going to make a change to my stack, I'm only making a change to the child stack. I'm not making a change to the parent stack. So our output here is going to differ because these two different processes have two different stacks now. They have different memory that's attached to them. All right, so I'm going to save this file. I'm going to push these changes up to GitLab. And what we're going to do is on Tuesday next week, we will spend a little bit of time talking about the term test. I'll come to you in just a second. We'll spend a little bit of time talking about the term test. And then we're going to spend a little bit more time thinking about what our process and what our operating system are doing with each other. And then we're going to add one more thing to this process management stuff, which is to be able to ask questions about the state of our child process and be able to run other programs. Yeah. So the question is specifically about strace and whether or not we'll print out the system calls made for the child and the parent process. It doesn't by default. So when I run strace here, it's only going to print out the output from one of them. And so you can see here that we've got the right for 42. We see that 80 is printed, but it doesn't actually show the right system call for that. So you have to pass an option to strace, which is follow -- follow forks. And that says follow all of the children that get launched by the process that you started operating on. So we'll do that next week. And then at this point, you should be able to describe what a human operator might see in files when a file system is in an inconsistent state. You should start to be able to describe the life cycle of a process in terms of states. When I start my process up, it's running. When it's waiting for input, it is blocked, and then it will go into an exit state. And you should be able to start to do this, but we'll continue along with this next week. I hope otherwise that you all have an excellent long weekend, and I will see you next week. Bye, everyone.